Hello guys, this is our presentation for ECE 176 for our final project, which is about robust detection of occluded pedestrians in autonomous vehicles. So we saw that performance of detectors drops significantly when objects are partially occluded. And in the realm of autonomous vehicles, this is super important because you need robust models that can identify even subtle things that can mean the difference between life and death regarding early detection of any like issues that they might run into in terms of running into a pedestrian or running a red light, stuff like that. So our idea was to implement data augmentation through synthetic occlusion, which is a simpler model that doesn't rely on a lot of memory or a lot of data compared to other solutions that have been developed in the past. So that this involves like using occlusion to synthetically basically identify pedestrians from individual features rather than just like the pedestrian body itself. And here's our methodology. So step one was our collecting our data set. Step two was developing three separate data sets that we will talk about later. And then training separate models on these three data sets. And then applying three models onto a plain test set. And then some occluded sets as well as real world images that we collected over the UC San Diego campus. And then evaluate our results. So for data pre-processing, we had the Caltech pedestrian dataset that's open source and that contains a lot of images. So we decided to subset the dataset and collected a total of 21,000 images and had an 80 to 10 to 10 train validation test split. And for data augmentation, we decided to have two additional augmented datasets that were applied some synthetic occlusions like black mask augmentation and noise mask augmentation. So setting pixels to 0, 0, 0, and then setting pixels in the bounding box to random values. And augmentation was applied to about half of the training images, and there was a uniform chance of covering 20%, 40%, or 60% of the pedestrian bounding box, and the uniform chance of occluding top, bottom, left, or right of the pedestrian. For training, we had three different data sets, the baseline data set, black mask data set, and mask data set. And we fine-tuned YOLO V8s using 30 epochs, an image size of 960, and a batch size of 8. And this produced the best result on the validation set. And yeah, then we tested those three different models on four different test sets. The baseline, the synthetically occluded data set with black masks and noise masks, and real-world occlusions.
So moving on to the results, this is a bar chart that shows four different metrics that we tested our model on. And as we can see, the black mask actually performs the best on three of those metrics, precision, recall, and mean average precision 50 to 95. And we, but the differences were marginal. So we further looked at like the synthetically occluded test sets, and we found out that overfitting actually occurs. In the black mask data set, the black mask model was outperforming both the models, and noise mask data set, the noise mask model was outperforming. And we realized that this is because of it detecting the black rectangular boxes and the noise rectangular boxes rather than the human features. So moving on, we actually decided to collect our own data on ECSC campus and then test the model, and this data set contains pedestrians that are heavily occluded. And we found out that, again, Black Mask performs pretty well compared to the other models in a lot of those metrics. Let's move on to like a few examples of where it actually performed well. So over here, the pedestrian was blending in with the environment, and both of our augmented models actually caught that, while the baseline model failed to detect the pedestrian. However, it still needs some improvement. We can see that in this case, the noise mask augmented model um, actually does not capture the pedestrian in front of the car, but captures the pedestrian that's almost out of the image. Um, Another case is hallucinations. So in this case, it's hallucinating that there's a pedestrian in the center of the road. However, there isn't. And that's probably due to like the noise augmentations being too aggressive. So in conclusion, um, the augmentations do give us small improvements in precision and recall. However, to make it completely robust, we need to use larger models, train on more data, and increase the training epochs as well. Thank you.